Good afternoon, and very, very welcome at the last colloquium of this semester. Today it is a true honor to introduce Eva Ostriker. Eve is a widely known, world-respected expert in the area of star formation, stellar feedback, and the interstellar medium, from small scales within molecular clouds all the way up to galactic scales and galactic winds. And Eve did her PhD at the University of California in Berkeley, got it in 1993, then did a first postdoc there and moved on to Harvard, where she was a CFA fellow for 2 to 3 years, and then became a faculty member at the University of Maryland. Since 2012, you are a full professor at Princeton University, and among others, Eve is, as I mentioned, extremely well known and has won a huge number of prizes, of which I'll highlight two, which is that Eve was a Guggenheim Fellow in 2009-2010, and also is a Simons Investigator now. And today, you're going to talk to us about, hopefully, as much as possible of that wide range of research that you do, and specifically talking about burning down the house, star formation and feedback in giant molecular clouds. So let's give Eve a very, very warm welcome.
So I think, thanks very much, Diedrich. It's an honor to be here and to be the only thing standing between you and exams and 2 months of winter break. So I was last here in 2011. Oh, and I should just say that this is just kind of a public service announcement to say don't let a star into your house, at least not a massive star, because they are very dangerous. So last time I was here was in 2011. I spoke about how star formation is controlled on large scales by feedback, and in particular the UV heating and supernovae are dominant in setting the pressure on large scales, and that pressure then has to maintain an equilibrium with the weight of the ISM, and that then can control the star formation rate. We've actually learned a lot more about this process since last time I was here, and I'll just show you since I'm not talking about this today, just a movie from what we've been doing on the large scale. So this is in kind of kiloparsec scale tall boxes, and we call this Tigris, which is basically saying we're doing the three-phase ISM and we're resolving evolution. So the resolution is quite important for this. We're getting down to parsec scales, and that's important in order to resolve the hot ISM, and we're interested in the hot ISM both for the ISM itself, but also for driving of galactic winds. And you can see here, this is velocity, and you can see that the gas is being driven vertically outwards in both directions from the midplane. That's driven by the hot gas, and it's the interaction of the hot gas that also with the warm gas that also creates a fountain. You can see that warm gas rises up and then it falls back down. And just as a point of comparison, you know, our resolution per cell in the hot gas is about 10 to the minus 4, 10 to the minus 3. For comparison, something that you might see in a Zoom simulation like fire is 10 to the 3 or 4, so that's 6 orders of magnitude. And in a simulation like Illustris, these kind of large box simulations, that's more like 10 to the 5 or 6. So there's a really big difference between doing a small box where you can resolve the physics and what you can learn there, and what you can afford when you're doing a global or a cosmological simulation. So to really understand what's happening in the ISM, you need to really resolve. And I don't want to talk about this really too much, but just to say that for these kind of simulations, there are a lot of science goals that we can go after with these resolved simulations of the ISM in terms of phase balance, the chemical state, relationships between gas and star formation, the ionization state as well. One thing we've been working a lot on recently is on galactic winds. And we have some papers coming out that Chang-Gu Kim has been focusing on, which will be done very soon. So some quite interesting results on driving winds and how you have to, those wind driving rates are actually much lower than is often assumed in cosmological simulations. Okay, but today I'll really be focusing on on much smaller scales, that is cloud scales in the interstellar medium. And what's shown here is a map from Planck. So this is a dust emission map. So this dust is heated by starlight, and then it's re-emitting in the infrared and submillimeter. And what you can see here marked is individual positions of relatively nearby clouds that stand out. Here's Taurus, Ophiuchus, Orion. So Orion is actually a much more massive cloud, but it's further away by a factor of more than 5. So it appears the same size in the sky. Molecular clouds come in a range of sizes and masses. These clouds are of the order 10 to the 4. These are of order 10 to the 5. More massive clouds can range up to 1 million solar masses, or complexes up to even 10 times that. So that was a dust emission map. Another way to get at the properties and of molecular clouds is using dust extinction. So you look at background stars and you see how much the light is extincted by the dust in the cloud. And these are both extinction maps for some of the same clouds that I showed you previously. Here's Taurus, here's Orion. And these are kind of the typical what is often defined as molecular cloud properties of being above AV of 1, column density more than around 10 to the 21, and these kind of masses. So, but neither of those ways is kind of perfect for getting at what is the total mass in a cloud. Perhaps the best, least ambiguous way of getting at what the mass in a cloud is, or the surface density, is to use multi-wavelength dust emission. So if you have a number of different frequencies, then you can really get at what the total column is by modeling that dust. Okay, so, but of course, dust is only 1% of the mass, so most of the mass is in gas. And when are these the ISM is all gas. When is that gas molecular? And so what I've shown here is that this is as a function of column and as a function of density. Where do you have molecules? Because molecules can be destroyed by UV radiation, so you have to go to either high enough density or high enough column density so that the UV does not penetrate. So that's kind of determined by what's called the shielding length, and the shielding length depends on the density and also on the radiation field. So this is kind of solar neighborhood radiation field, that's 10 times higher, and that's 10 times higher. The other thing that determines whether there are molecules or not is whether the cosmic ray rate, because that can destroy molecules as well. And so this is a low cosmic ray rate. This is what we think is kind of typical, and this is about 10 times that, or 5 times that. So you can see that the region the solid line here in each panel is where 90% of the gas is in molecular hydrogen. And of course, we don't look at clouds in molecular hydrogen, we look in CO, so that's shown in this purple solid line there, where 90% of the carbon is in CO. So we expect to see molecular clouds in molecules in this upper part of the diagram. In principle, if you went all the way to equilibrium, you could actually have H2 clouds down here. But in fact, the dynamical times are short enough that gas would get re-exposed to UV before reaching equilibrium. So we really only expect molecular clouds in this corner here. And but one thing to notice is as you change the environmental conditions, going to higher radiation field or higher cosmic ray rate, you change the conditions of what a molecular cloud is. Okay, so when using molecular emission, of course, then you get information on velocity, and so you start learning something about the dynamical state of these clouds. And what's been known since the 1980s, when molecular clouds were first studied, first at low resolution and then with much higher resolution mapping, is that they're energetically dominated by turbulence. That is, the line widths of molecular lines are much broader than the thermal line width which you get from the relative excitation of different levels. They also have significant magnetic fields. I'll get back to that later. And they appear to be at least close to gravitationally bound in the sense that their velocity dispersion is kind of comparable to g m over r. But again, that's not an exact relationship. So I mentioned that there's now a much higher resolution than there was in early days. This is from an extremely high resolution map of the Orion cloud. So this is just this red part of the Orion cloud. This is down to 0.01 parsec resolution with 1/10 of a kilometer a second velocity channels. And you can see tremendous structure in these clouds. One of the characteristics of turbulence in molecular clouds is that it's dominated by the large scales, and it has a power spectrum that increases as roughly the 1/2 power of size. So that's what's shown here, the velocity dispersion versus size relationship. And it's only when you get down to quite small scales, 1/10 of a parsec, that the velocity dispersions are below thermal values. So these are, they're kind of extreme laboratories for compressible turbulence. Of course, as everyone knows, GMCs are not just interesting laboratories for turbulence, but they're also interesting because that's where stars form. And what's shown here is different views of Orion. Here's the molecular gas, but here you can see the in the optical, the stars that actually formed in the ONC. And then this is already showing you some of the effects of those stars in terms of the dust emission, both in mid-infrared here and far infrared. So this dust has been heated locally by the stars and then is warmer than it would otherwise be without the nearby star formation. So, and this is just a kind of another view of Orion showing the zoom in on the cloud, and that the stars are really only forming in the densest portion of the gas. So there are stars forming everywhere, but really the clusters form in the densest part of the gas. So one kind of basic question is, if you have a cloud, what fraction of its mass will go into stars in its lifetime? That's actually a somewhat difficult question to get at, because when you look at a cloud, it's not either at the beginning of its life or at the end of its life. At the beginning of its life, it has 0 stars in it. At the end, the gas is gone. So it's actually somewhat difficult to get at what the lifetime intrinsic star formation efficiency is, which would be the total stars formed over the intrinsic is the total stars formed over the initial gas mass. What you always see instantaneously is this. So you have to do something statistical to try to get at what the lifetime efficiency is. In the case where you have steady star formation and the cloud is destroyed rapidly compared to its lifetime, in that case, the observed star formation efficiency would be about on average, would be half of the lifetime star formation efficiency. So if you kind of use what I've shown here as a guide, that would amount to something like, the observed range can go very low, up to somewhat higher values here, but typical values might be a few percent if you just kind of use that typical value to keep in mind. Orion is 1%. So now that's looking at individual clouds in the Milky Way. You can also do this. You can also get at this question using extragalactic observations, and a number of people here, probably, I don't know, I haven't counted, 10 people in this room may be involved in these kinds of studies of determining both the star formation efficiencies and also the timescales for evolution within clouds. And one of the ways this is done is by looking at, and what I've shown here is a version based on Eva Schinnerer's paper, where you look at how much gas is there without stars, how much gas is there that has stars, and then how many, in a map, how many regions are there, the fraction of the map that has no gas. So that will tell you essentially the fraction of the life cycle that a cloud, that is spent in these different regimes. That is, this first part is kind of inert. This is the feedback regime. How long does it take for stars to form and then destroy the cloud? And this is the kind of the recollection time when there is no gas where you have stars. And there are different ways to do this with different levels of complexity, but the kind of numbers that come out of these kind of studies are that the onset timescale for star formation is on the order of 5 or 10 million years, which is a few times the freefall time, 1 or 2 times the freefall time. The dispersal time, so once you have stars, how long does it take to destroy the cloud, is again on the order of a few million years, but typically slightly shorter than the onset time. And then the lifetime star formation efficiency that you get out of this by taking that lifetime and multiplying by something like the global star formation rate divided by the global molecular content is on the order of a few to 10%. So that kind of gives you an empirical relationship, which is somewhat similar to what's seen in the Milky Way. So this is just showing you, again, a star-forming region relatively near 2.5 kiloparsecs from the sun, the Carina Nebula, which is a very well-known star-forming region. It has about 70 O stars in it, much more luminous than Orion. It's about 150 times the luminosity of Orion. And you can see clearly here, again, the effects of the stellar feedback. So here you see all of these emission lines, O3, H-alpha, sulfur 2, and this is the infrared heated dust. And what's shown here as well in this complex is the positions of stars in clusters. So these are each an open cluster. So here, one of the things about Carina is it has this most luminous star in the galaxy, Eta Carina here, and a lot of other stuff happening. This is a beautiful HST picture. I think this is hanging up on the wall on the hill. And you can see, the reason I wanted to show this in addition to it being beautiful is that you can see these individual dark regions that have bright edges. And those edges are bright because this is where gas is being photoevaporated from the surface of a dense region. And you can see that happening directly. And you'll see that in our simulations in a little bit. Okay, so clearly feedback is happening. It creates beautiful pictures that you can make posters of, but it's actually kind of necessary from the point of view of if there weren't feedback, there would be nothing left to study for observers, and for theorists, we kind of have to take it into account because the timescales of the heating and cooling and the turbulent dissipation are very short. So it's kind of necessary aspect of understanding the interstellar medium and taking that into account. Okay, so what are some of the forms of feedback that in principle we should take into account? I've listed kind of comprehensively here, and you can read about this. Mark Krumholtz, who's here on sabbatical, has a review on this. So I'm not going to go through all of these in detail, but just to mention, there's certainly radiative heating, as I've described. There's heating by ionizing photons, as well as photoionization. There's the direct radiation force of photons being absorbed by dust, and then that gives them a kick because photons have momentum. Also, the photons can be absorbed by gas in ionizing them, and that gives a direct kick as well. There can be winds from stars. Supernovae, as shown here, are quite important, especially in the later stages of evolution of a star cluster. And cosmic rays actually can be important more on large scales, but as I mentioned, that's also important for the molecular, whether some gas is molecular or not, and more generally, the chemical state. So let's see. So I will not really I won't be talking about winds today. There are a number of kind of classical studies of the effects of winds. Winds seem to be less important than you would naively expect, kind of empirically. So a number of people have looked at that. And the basic reason for this is that probably that the hot gas at the edge of the bubble is mixing, the shocked wind bubble is mixing with the denser gas, and then there's a lot of losses to cooling, as well as the fact that hot gas can easily escape through holes in the cloud. So the things that are shown in red here are what I will really be focusing on. That is the effects of radiation. And of course, radiation, we know, is the largest fraction of the energy that a star makes actually is in radiation. Over its lifetime, a massive star will return 10 to the 53 ergs of energy to its surroundings. Most of that is actually in UV, not is in UV, not far UV, not ionizing UV. But in fact, the ionizing UV is more important, as I'll argue. Okay, so before I kind of get into the gory details, I'd like to show you a movie, what's shown here, of the effects of radiation in a cloud. So we have this turbulent cloud, there's localized collapse, and as a result of the localized collapse, we substitute for the collapsing regions sink particles, which then have a luminosity according to what you would expect for a cluster of that mass. That radiation then we do the radiation transfer for that radiation to interact with the surrounding gas. That can ionize gas and also apply a radiation force to the gas. And you can see as soon as this starts to happen, you start making this ionized gas, and that ionized gas will expand rapidly and push on the remaining neutral gas. So that's via the rocket effect, essentially. Yes.
Approximate physical scale of that simulation?
So this scale, the initial cloud was 40 parsecs across. Okay, so to get quantitative, we will return to some of the basics that from everyone here has taken a course in astronomy, so everyone knows what a Stromgren sphere is. And so actually, a Stromgren sphere is quite useful for understanding these more kind of it's not really a Stromgren sphere, but actually all of those scalings turn out to be quite important in understanding the true evolution in this more complex case. So if you have an ionizing photon source, you expect that all of those ionizing photons will be absorbed, and then that absorption rate has to match the recombination rate of the protons and electrons recombining with each other. So you can balance this Q with the recombination rate, which just depends on volume and the density. And initially in a cloud, you could say, okay, I know the density, I know Q, what's the radius of the Stromgren sphere that's ionized? So that's what happens initially. Of course, this is overpressured by a huge factor, a factor of 1,000, so it will expand. Here's the expanded version. And once it's expanded, what you actually can think of is, well, you know what the radius is, so what's the density inside such that Q will balance the recombination rate inside, because you're basically photoevaporating from the inner surface of the cloud to fill in the interior. And so then you expect the density to scale as the square root of Q and the minus 3/2 power of the size of this ionized bubble. And Spitzer, back in 1978, worked out the solution for an expanding H2 region based on just applying the pressure to the shell, and the shell expands and sweeps up surrounding material. And what's shown here is Spitzer's solution. Okay, so what Spitzer didn't include is the fact that radiation pressure actually modifies the interior structure of an H2 region. And what's shown here is from Drain's solution. That is, if you just look for the equilibrium solution where you allow for both radiation pressure and ionized gas pressure, you rearrange the interior of an H2 region. What's shown here is the profiles of density at different values of Q. So this is a low value of Q times density, that's a high value. So in the case where the radiation field is very strong or density is high, all of the material gets pressed out to the outside, and the interior has a very high radiation pressure. So these are the corresponding runs of radiation pressure. So that rearrangement means that the radiation pressure will be large at small r, the gas pressure will be large at large r, the pressure will be uniform in the interior, but you've done that by rearranging the material. And then you can ask, well, what's the total force going to be on the shell that surrounds this? And so you can, basically solve this equation and then work out what the force is. And that's what's shown here in black. And then it's actually quite a good approximation to what you do if you just take the 4 pi r squared times the temperature times the density, assuming equilibrium, that's what's shown here, and add it to L over C. So that is actually a quite, the sum of those two is actually very close to the exact solution. And that was what Krumholtz and Matzner worked out is what's the characteristic radius where these two, the gas pressure, which is this one, and the radiation pressure are equal. So there's a characteristic radius which depends on Q. So Q is very small unless you have if you have a significant mass cluster with many O stars, then that characteristic radius can become significant. Okay, so if you allow for radiation pressure, that actually modifies the evolution of even a simple H2 region. And so this is, what the evolution equation would look like, different from what Spitzer did. And you can again see that the radiation force term is dominant at r equal, for small r. And then if you substitute in here, this increases as the 1/2 power of the radius of the H2 region. So this becomes more important at large radius. And so you can imagine if you kind of allow this to evolve, what's the criterion for the cloud to be disrupted? Well, the criterion has to be you have to have large enough L and or Q such that the velocity when you get to the edge of the cloud is larger than the escape speed. So that would be kind of a very simple model for what would determine the star formation efficiency. There has to be some minimum luminosity that allows disruption. So you can ask what the scalings of that would be. Here's a simple version. If you just include radiation pressure, that total momentum per time scales with the mass of the cloud times the efficiency, the fraction of that you've turned into stars, and then that's luminosity per mass, which is about 1,000 solar luminosities per solar mass. So that momentum per time would have to exceed the gravity in order to destroy the cloud. So you can, work through the algebra and show that the efficiency, you'd expect to have some efficiency that increases with the surface density of the cloud. So you'd expect higher efficiency when the surface density of the cloud is higher. So you can do a similar thing just thinking about if you had only the pressure of ionized gas. Here you can essentially work out what the force is, assuming ionization equilibrium, again, assuming that some fraction of the cloud has been turned into stars, which is this efficiency, and then equating that to the gravitational force, doing the algebra, and that says that the efficiency would increase with the cloud surface density and a little bit with the cloud mass as well, but mainly depending on the surface density. So here, this is shown if you actually do the full evolution of an idealized H2 region, including both the radiation and the gas, and then you ask, what efficiency would you predict in this idealized case? Here, if you have a kind of typical cloud like Orion, which has a surface density of about 100, mass of 10 to the 5, you'd expect something like an efficiency of a few %. So that might seem good. Okay, that's the observed efficiency, so we're done, go home, study for your exams, grade your exams. So that would suggest a relatively low efficiency. I'll come back to this in a bit. Because actually, of course, clouds are not spherical, so you don't have a closed shell. And when clouds have holes in them, which the stars themselves can create, the gas can photoevaporate and escape through the hole. So basically, this gas is very overpressured, and it can expand and leave the cloud. And so if you have essentially a surface that's irradiated by the star, gas will stream away from that surface after being evaporated at basically the ionized gas sound speed of order 10 kilometers a second. So then the rate at which you photoevaporate depends on the density, the sound speed, and the area. Here, this semicircular area. And that then gives you the photoevaporation rate. And so if you take that, you can also work out what the back reaction force is. Given that photoevaporation rate, it kicks back on the cloud, pushes the cloud, and you get essentially the same thing as for that force as you get for the closed H2 region. So what would then you expect for if you're photoevaporating gas, given the photoevaporation rate and assuming some lifetime that scales with the dynamical time of the cloud, you might expect to have an efficiency that, if again you work through this, that scales with the square of the surface density of the cloud. So again, the expectation is the star formation efficiency will increase for higher surface density clouds. So those, there's different scalings for each case, but the overall expectation is higher star formation efficiency at a higher cloud surface density, with that being the primary variable that determines the efficiency. So, of course, those are, nice ways to get a physical appreciation for the problem, but we'd like to really be able to get quantitative numbers for this. And for this, there's no substitute for doing numerical simulations because clouds are, in fact, highly inhomogeneous, so the radiation can escape through holes. There's also a large range of the, all of those analytic estimates include a given surface density and a given density, but of course, they have a wide range of values. And so we need to have numerical simulations in order to actually get accurate ideas of what the evolution and the outcomes are for these processes. So what we have done in my collaborators and I have done, led by Jongyu Kim, is to follow for clouds, which we have a kind of idealized prescription for, that the gas is replaced by star particles, as you saw in this simulation, which have both ionizing and non-ionizing photons. And I won't go into the details of this, but we use adaptive ray tracing for following the radiative transfer of the radiation, starting with, so we use heel picks for splitting the rays. That's what makes it adaptive, starting with heel picks level 4, and then we split the rays when there are fewer than 4 rays per cell. So we want to resolve the radiation that's going through each cell. So just one additional comment on this is that, if you think about ionizing radiation, it has an extremely large cross-section, so you want to get an accurate measurement of the radiation field, because if you have an inaccurate measurement, you can be very far off in terms of your prediction. So I think it is quite important to have an accurate radiative transfer method. Okay, so here, this shows the evolution of the same cloud that I showed you before, which is kind of like Orion in its properties. What's shown on the left here is gas surface density projected. Those are the locations of the star particles. What's shown on the right is the emission measure, so the integral of NE squared into the plane. And you can see that what's happened, of course, is that you form stars and the cloud gets dispersed over time. This shows some snapshots of the evolution of this cloud. You'll see that initially there are these very bright regions, so those are, the gas is very dense initially surrounding these star particles. Over time, that gas is pushed away, and it starts to look like a more classical H2 region in the sense of having bright-edged surfaces, globules, and kind of pillars. So the kind of features that you could see in this map of Carina. So one other thing I'll mention is that actually stars can be formed at later times in the globules here. Some people have interpreted this as triggered star formation, but I would actually say that it's not triggered star formation. It's just that star formation can only form where there is gas. So stars can only form where there is gas, and the gas has been pushed away so far that that's where there is gas available. So overall, this is not triggering, but this is actually quenching star formation. So here you can see on the right a kind of overall evolution of what's going on. So the gas mass within the simulation volume is decreasing. The mass of ionized gas is increasing because of the photoevaporation. This is actually including gas that has left the computational volume. And the stars are building up over time. So this is about a 13% final star formation efficiency. Much more gas is lost in the ionized form than the neutral form. So really this is photoevaporated rather than being dynamically destroyed. Another thing that's kind of interesting here is the evolution of the escape fraction, because the photons that are not burning down the house are actually getting out of the house and doing things in the rest of the galaxy. So the escape fraction in this cloud is typically about 40% for both the non-ionizing and the ionizing photons. And I'll come back to that later. Okay, so we can do a comparison of doing the only non-ionizing, only ionizing, or both, and that's what's shown here. So the stars are both, the squares are radiation pressure only, that is non-ionizing only, and red is ionizing only. And you can see that the star formation efficiency would have been higher if we hadn't included, if there were only radiation pressure. And essentially, the addition of, if you have the photoionization and you also include radiation pressure, so you go from the red to the star, it makes a little bit more of a difference, but really not that much difference. It starts to be more of a significant difference when you get to very high surface density. So you'll remember that I had this, expectation that that radiation pressure becomes more important at larger Q and at larger surface density, and you see that effect, but it really only starts coming in at the very highest surface densities here. I think I'll skip that. And this is just showing the characteristic velocities of the material that's leaving. So the ionized gas typically leaves at 20 or 30 kilometers a second, whereas the neutral gas typically leaves at about 10 kilometers a second. So one of the things that's interesting to quantify is, so I started you out with some simple analytic expectations for, if you have an H2 region, what does that H2 region do? So you can actually make the comparison between what we find in the simulation of what the pressure is from what the gas pressure is from, the ionized gas pressure integrated over the volume, and what the radiation pressure is integrated over the volume in comparison to the simple expectation. So the radiation force would be just L over C, and we can compare that to what we measure for the radiation force. Similarly, we can measure the gas pressure force and compare to this kind of analytic estimate that I gave. And that's what's shown here in these colored circles. So the red is the thermal pressure force compared to the simple analytic expectation. The blue is the radiation pressure force, again, compared to L over C, and you can see that you're down to about less than 20% of the analytic expectation. So they both are. So the thing to notice about this as well is that it's relatively independent of the surface density. It's relatively independent of the properties of the cloud, but it's significantly reduced to compared to the simple analytic expectation. So, but because you see that that's kind of independent of the properties of the cloud, that suggests that we can get a modified version of an analytic solution for what causes the cloud to be destroyed. And you'll recall that most of the destruction is via photoevaporation. So we can ask, well, what was the scaling expected for photoevaporation? So the expected photoevaporation rate will just scale with the density and some area where the density is determined by ionization balance, ionization recombination balance. And if this area scale, the ratio of the area to the thickness of the photoevaporation region scales with radius, then this is what you'd expect for the photoevaporation rate. And we can then check, well, we can compare the photoevaporation rate in the simulation with this, which is just set by the total cluster luminosity and the cloud size, and we find that indeed that factor here, which is essentially a calibration factor, is relatively constant across these simulations. So that means that we can have an expectation for what the total mass loss is to photoevaporation. That's what's shown here in the dashed line, and that's actually quite close to what we find. And this is comparing the fraction of the initial cloud that goes into photoevaporation. Again, this is the analytic expectation shown with the dashed line, and that actually agrees quite well with the numerical results. And I'll just mention here that the net momentum that you get from this kind of process of the radiation feedback is typically only of order 100 kilometers a second if you compare the momentum to the mass. And that can be compared to something like more like 1,000 for supernovae. So overall, this radiation feedback is subdominant compared to supernovae, but it's important because it happens fast. So this is, in the parlance people often use, is early feedback. This happens, of course, before supernovae, and that means that it's, that can actually do a lot towards destroying clouds before supernovae ever come along. So I mentioned that there's a new understanding of much better measurements of evolutionary timescales of clouds from the work that many people here are doing in the extragalactic realm. And I'll just show here that we find timescales that are indeed relatively short, that is comparable to the dynamical time in clouds. So the destruction actually happens quite rapidly. Okay, but coming back to the net star formation efficiency, so here, if we look at a cloud like Orion, it's of order 10%. That seems a bit high, so that may seem high to you. It seemed a bit high to us, and so, what might we be doing wrong? So one thing that we might be doing wrong compared to real clouds is that in the simulations I just showed you, we weren't including magnetic fields. And in fact, clouds are significantly magnetized. So this is just showing that the magnetic fields are actually close to critical in the sense of where critical is defined by having magnetic support, basically entirely compensating for gravity. And so clouds seem to be significantly magnetized. So we've been looking at, if you allow for magnetic fields, how much does it change the results? So what's shown here is going from a moderate magnetic field up to a strong magnetic field. Each column is a different simulation, and then each row is a different projection of that simulation on the plane of the sky. The two right ones these are subcritical, these are supercritical, that is weaker fields. And you can see that in the case of weaker fields, you form fewer stars, but the evolution is slower. And quantitatively, this is showing the star formation efficiency after 3 million years, which is kind of nominally when you might expect supernovae to start. And this is the star formation efficiency if you just allow this to go until all of the gas is removed. And each of these colored lines here represents a different seed. So since this is a turbulence, there's a different realization of the turbulence. So we looked at, well, after all, there's not just, since turbulence is turbulent, there's not just one turbulent cloud of a given energy. There's many, infinitely many turbulent clouds. So what we did here was we tried different realizations of the turbulence. And that's what's shown here. And you can see that actually, when you vary the initial turbulent realization, you will actually get a different efficiency, which is interesting in itself. But the other point here related to the magnetic fields is at a stronger magnetic field down here, the star formation efficiency is significantly lower than at a weaker magnetic field. So whether you look at the efficiency after 3 million years or the lifetime efficiency. So one thing that can actually get you into the range of observed clouds of a few % efficiency is magnetic fields. So another thing that is a fair question is, we were starting with a cloud that's marginally bound, but after all, are clouds bound? There are some reasons to think that they may not be, in fact, bound, because when people make estimates in observations, typically what they're doing for the gravitational energy is they're basically just using GM over R, treating the cloud as if it is isolated. But real clouds aren't isolated. They live, and they're not spherical, so they live in an environment where there are other clouds, and the tidal forces effectively reduce the binding energy of the gas. So the true virial parameter, the ratio of kinetic, twice the kinetic to gravitational energy, may be higher than the simple estimates would suggest. So it's it's worthwhile actually exploring whether the initial the initial variable parameter significantly matters. And another thing that motivated us to do this is that when we look at the clouds in our galactic scale ISM simulations, we find that basically they are generally only somewhat bound. So the densest part of the clouds are bound, so at high density they are typically bound, but the more massive clouds are generally not bound at moderate density. And what's shown here is if we define clouds based on a contour of density, and then we ask what fraction of it is actually bound if we use the true gravitational potential, which of course allows for tidal effects, what's shown in color scale is the fraction of the cloud by mass that is bound. So, if you take a typical cloud density, only the more moderate mass clouds would be entirely bound, and the higher mass clouds would not be bound. So this, I would say, is a caution that what looks bound, if you do the simple way, it may not be really bound. So this is also motivation for us to look at the case of if we allow for initial kinetic energy that may be somewhat higher, what's the result on the star formation efficiency? So this is, again, a series of simulations where on the right is higher initial kinetic energy and different projections. This is lower kinetic energy. And you can see that at higher initial kinetic energy, the cloud actually evolves more slowly, but it forms fewer stars. So it only has the kinetic energy it started with. It doesn't have much feedback, but not that large a fraction of the cloud gets turned into stars. So again, there's a decrease in the star formation efficiency, which can get you into the observed regime if you get to a variable parameter of a few. And I think combining the effects of magnetization and having a variable parameter that's probably more than one can get you into the range of observed star formation efficiencies. So, but another thing that we're not including here is we're not including supernovae. And in fact, supernovae can destroy, if you still have material around once supernovae start to occur, then you can actually, even with a quite modest star formation efficiency, you can reach an ejection velocity. So, of comparable to the velocity of a cloud. So that, I think, suggests a possible scenario in which radiation takes the job a large fraction of the way, maybe not quite all the way, and then supernovae finish the job off. Okay, I'll skip that. So finally, I'd like to say a little bit about what happens to the photons that don't burn down the house, that is, the ones that do escape. And what's shown here is for several different, these are different cloud models, and what's shown here is the escape fraction in orange of ionizing radiation and in blue of non-ionizing radiation. And one of the interesting things about this is these escape fractions are actually quite similar. So although you might have thought that they would be different, in fact, for this regime, it's more like having holes in the cloud, and the radiation can escape through those holes, whether or not whether it's basically set by the dust rather than by the gas absorption coefficient. So the escape fractions are, of order 40% or so. So that's a significant escape fraction. So one of the other aspects of this is that the escape fraction is much higher than it would be for a spherical cloud, or for that matter, a cloud where you're modeling it, but you're not resolving it sufficiently. You're not resolving the turbulence, so you're not resolving the structure. And what's shown here is as a function of the optical depth given just the external cloud surface density, the true escape fractions shown in circles here. And what you would expect if you just took that, average cloud surface density and multiplied by the dust opacity, that's what's shown here. And you can see that the true escape fraction is much higher than the escape fraction that you just predict using the uniform cloud properties. In fact, it's closer to, if you reduce that by a factor of 10. So it really makes a big difference because of the exponential attenuation of radiation. So you can make an estimate for what the escape fraction would be if you, which you could then apply in observation. So if you actually are able to resolve the cloud and you can see, exactly what the distribution of dust column density is, then you can make an estimate of what the escape fraction would be by averaging over that PDF that you observe, or alternatively, if you don't resolve the cloud and you just have some average value for its average value of the optical depth, which is basically just this, then you can still make a reasonably good estimate. That's what's shown here as a solid line of what the escape fraction is. So this is kind of a poor man's estimate for the escape fraction if you just have some rough estimate of what the column of dust is for the cloud. So and just to wrap up, I'll show you, what happens to these photons when they escape. Well, they're interacting with the rest of the ISM. And what's shown here is when we take our Tigris simulations and then we're doing post-processing where we allow the photons to propagate through the whole simulation domain. And what's shown here is the emission measure. This is projected on the plane, and this is if you just project it, looking at it sideways. And here, this column over here is showing the ionized fraction. So this is basically showing you that you can get ionized gas at above the disk. Basically, the radiation can traverse the disk through holes which are made by, essentially by the chimneys of hot gas that are escaping. And this can produce this ionized atmosphere above and below the disk. So that can be seen as what is, a fountain layer is partially ionized, or what is has been described as the Reynolds layer from the first from Ron Reynolds' first discovery of this in, I don't know, maybe the late 70s. Okay, so I think that wraps up, and I'll put my conclusions here. I think this is close to on time, so I'll stop here.
Thank you, Eve, for a fascinating talk. I open the room for questions, and I go up immediately. Good.
Thank you very much for this wonderful talk. There's wonderful calculations with the radiation transfer. I'd like to ask about the simulations where you have the magnetic field as well as the radiation and the the viral overshoot. You said that the lifetimes increased. Typically, I didn't catch the sort of lifetimes that you might achieve there. Was it?
Yes, I guess I think. I don't have the numbers in my head, but it can increase the timescale by a factor of a few. So I would say that the realistic value is kind of in between, where this is. I'll run the simulation again. So I think the more realistic value is someplace in between here. So you can. Let's see, you can see the clock up here.
I can't quite, but yeah.
So it's about 10 million years.
All right, that's interesting because the simulations we do, interpreting data in terms of escape fractions and lifetimes, require those sort of numbers, 40% escape and maybe 10 to 20 even mega years, a little bit more than most models use.
Trouble seeing with the projector. I have a question while other people are getting inspired. So you showed a lot of star formation efficiencies as a function of parameter space for isolated clouds.
Yep.
Now I envision if you put those in an environment like Tigris, the fact that they're sitting in this external environment where other star formation events and also turbulence can influence them, that would actually change those scaling relations.
Well, so that's the question of is the cloud essentially destroyed before, before something is it destroyed by its own internal processes before something comes along from outside to wreck it? And so that's, I think that's a very important question, which we, have not addressed yet, but we wanted to first get to, how much can the radiation do by itself, because that is what we have the most evidence for. So I think I would say that. And so we can get to, in terms of the star formation efficiencies, I think that they may still be a bit higher, which suggests there's still a role for for supernovae, whether it's from the cloud itself or from external nearby clouds in kind of the final solution for dispersing clouds.
So basically, the nonlinear coupling you find between feedback processes internally would also apply to external ones at some level.
I mean, I think it's different because when you're talking about the global environment, it's when you're talking about the global environment, you're really I think it makes much more sense to talk about a star formation rate, sure. averaged over many clouds, because whether clouds all have the same surface density at a given location or not is I think unclear. But certainly cloud surface densities increase as you go to higher surface density environments.
Yeah. Okay. Sorry. Yep.
I'm curious if you expect, obviously this is a very thorny, intertangled problem, if you expect the other bits of early feedback to change these scalings. So stellar winds, jets, obviously these early processes, unlike the early ones in supernovae, they're all going off at the same time into each other's residue.
Yep.
Do you have any plans to kind of throw everything in the kitchen sink at this, so to speak?
I mean, I think if you actually, you can look at how much feedback you get in terms of, the winds from low mass stars, and that's not that significant. From winds from high mass stars, the empirical evidence, from work that Mark Krumholtz and his student did, is that there's apparently much of the energy has been lost. So you don't see that effect in the kinetic energy. So most of the energy appears to have been lost. So that's down around, I don't know, the number is like 10% or something like that is remaining. So at least in kind of where you observe it, there's not that much X-ray emission, and you don't see that much kinetic energy. So it seems like a lot of that energy from stellar winds is lost. On the other hand, when you go to a more extreme environment, as I said, you only get velocities of 10 to 30 kilometers a second. So if you're in a region, a cloud which is like a starburst cloud where the density is much higher and the escape speed is higher, that's not going to solve any problems. So there are some regions where your only choice is to use something that is relatively inefficient. So it may be that stellar winds and supernovae play more of a role just because the radiation just is not that effective in those more extreme environments.
Thank you. And just going back to the escape of ionizing radiation, in the cloud simulation, you get numbers like 40% or even above that. Do you have any clue what's going on when you put that in the Tigris scale simulation? How much of the radiation that escapes the cloud actually managed to escape the midplane?
So yes. So so here I didn't put the numbers here, but we found that overall the escape fraction of ionizing photons from this galaxy is less than 1%. So the ionizing photons still remain trapped. They don't escape overall. The non-ionizing photons, about 25% of them get out of the galaxy. And we also looked at, we're finishing a paper on this, which give all the numbers. I don't have them all in my head, but the fraction of the photons that are absorbed in the midplane versus the fraction that are absorbed at high altitude. So I think no, I can't remember, but actually, oh, I wrote it down, good. So 40% of the ionized gas mass is actually, above 200 parsecs. So kind of high altitude is, because the density is lower, so the recombination rate is lower. So even though a much smaller fraction of the recombinations are at high altitude, a large fraction of the ionized gas mass is there.
So just following up on that, so the 40% of the ionizing photons that escape into the Reynolds layer will become diffuse ionized gas with very, very different line ratios than you're going to get for H2 regions. Have you given any thought to whether the line ratios that you will predict for sort of global, large-scale observations of galaxies where you're not resolving individual H2 regions are okay? I'm a little worried that you might make your star-forming galaxies look a little bit too much like AGN.
Yeah, so in fact, most of the radiation, as I mentioned, doesn't actually get that far. So even if it's, escapes from the cloud, it's still, you can just see here that most of it is absorbed here. So this is emission measure, and most of it is absorbed still relatively close to the midplane, where the gas is fairly high density. So it's not where, basically most of that emission measure is not going to be from very low density environments. But yeah, it's important. It's absolutely important to look at the line ratios, indeed.